Imagine a robot that doesn't just roll around your workplace. It walks in like a new employee, picks up the parts you're tired of handling, and learns the job by watching. That's the bet behind Tesla Optimus, and whether you love it, doubt it, or can't stop thinking about it, one thing is clear: it's leveling up fast. Optimus is Tesla's humanoid robot project, built to operate in human spaces, using a human-like body plan, with the long-term goal of doing useful work safely, repeatedly, and at scale. Not a research toy, not a one-off stunt, a platform intended for real jobs. Here's a fascinating fact people miss. Humanoid form isn't about looking cool, it's about compatibility. Human buildings, human tools, human shelves, human doorways, they're all standardized around our bodies. A wheeled robot can be great in warehouses, but the moment you add stairs, tight aisles, mixed tasks, and hand tools, the just put it on wheels answer gets complicated. A biped with hands is the universal adapter. Now let's talk achievements. The moments Optimus went from concept to, okay, that's real. Tesla first revealed an early prototype publicly in 2022, and even though it was limited, it showed the core direction. A full-size humanoid with Tesla's design language and a focus on practical movement. Then came steady improvements: smoother walking, better balance, more confident arm motion, and, crucially, hands that started doing real object manipulation instead of just posing. The hands matter because hands are where robotics gets brutally hard. Walking is complex, yes, but dexterous manipulation is where the world stops being predictable. A box is easy. A bag is chaos. A cable is a nightmare. And if you want a robot to work in human environments, you need hands that can handle variety, not just one custom gripper for one custom part. One of the biggest Optimus milestones has been showcasing delicate pick-and-place tasks, handling objects on a table, moving them with controlled grip, and doing it with a posture that looks increasingly stable and natural. That may sound small, but in robotics, small tasks are often the ones that take years to get reliable. Another key achievement is the direction Tesla keeps signaling: the robot should learn tasks in a scalable way. In the real world, factories change, processes change, products change. If every new task requires months of custom programming, you don't have a workforce, you have a science project. The dream is faster onboarding, demonstration, imitation, refinement, repetition. So what can Optimus do? Or what is it being designed to do when it's actually useful? Start with the obvious use case: repetitive, ergonomically punishing work. The kind of tasks where humans get sore backs, strained wrists, or fatigue from doing the same motion thousands of times. Think moving bins, sorting parts, loading items into fixtures, light assembly, packaging, and material handling inside a facility designed for people. If a humanoid can do these reliably, it doesn't just save time, it changes injury risk and staffing constraints. Next, mixed tasks work. This is the zone where automation usually breaks down, because the tasks aren't identical every time. A human might walk to a shelf, grab the right item, carry it, place it in a tote, return, then do a different thing 5 minutes later. Humanoids are appealing here because they can, in theory, switch tasks without rebuilding the whole cell. And then there's the underappreciated use case: night shift continuity. If a robot can run simple routines when the building is quiet, restocking, staging, tidying, moving materials to prep for the morning, you're effectively extending productive hours without asking humans to live their lives on a graveyard schedule. That's not sci-fi, that's operational math. Let's get specific about abilities, without drifting into hype. Optimus is being positioned around a few core capability pillars. 1. Locomotion that's stable enough for real floors, not perfect lab conditions. Real industrial floors with slight unevenness, ramps, clutter edges, and tight turns. Every improvement in balance, gait, and recovery from small slips is huge because it means fewer falls, fewer safety interruptions, and less babysitting. 2. Manipulation that's gentle and controlled. A useful robot needs to pick up a fragile object without crushing it, and also lift a heavier item without dropping it. That's grip control, force sensing, and planning. And it has to do it while the robot is moving, because in real work, you don't freeze like a statue before every action. You reach, you adjust, you place. 3. Perception. The robot has to understand where things are, what they are, and what's safe. This is where Tesla's broader experience with cameras and real-time AI is often brought into the conversation. But regardless of brand, the goal is the same: robust vision that handles messy reality, changing light, reflections, partial occlusion, unfamiliar items, and people walking through the scene. 4. Task learning and generalization. The holy grail is not one robot does one task forever. It's a robot can be taught new tasks quickly, then repeat them consistently. That's why demonstrations and iterative improvement matter so much, because it hints at a future where robots are configured more like software than like custom machinery. Here are a few interesting facts that put the project in perspective. First, Optimus is as much a manufacturing problem as it is an AI problem. A humanoid robot isn't one breakthrough. It's hundreds of parts that must be reliable, affordable, and maintainable. Actuators, joints, hands, batteries, thermal management, sensors, wiring, structural elements, and then the entire supply chain behind them. The difference between a demo and a product is usually boring, but it's everything. Second, the hands problem drives the timeline. Humans do ridiculous things with their fingers: tie knots, peel labels, pinch thin edges, separate stacked sheets, feel a misalignment, correct it instantly. Replicating even a slice of that safely at speed is one of the hardest challenges in modern robotics. Third, safety isn't optional. A humanoid working near people must be designed around controlled forces, predictable behavior, and rapid fault detection. That means the robot should move with intention, avoid sudden jerks, and default to safe states when uncertain. The most impressive robot isn't the one that moves the fastest, it's the one that earns trust. So where does Optimus go next? If the project succeeds, the near-term story is not a robot doing everything. It's a robot doing a few valuable things extremely well, inside controlled environments, then expanding outward as capability and reliability grow. Think factories first, then warehouses, then other structured workplaces. And long-term? The reason this project captures attention is simple. A general-purpose humanoid, produced at scale, changes the economics of physical work the way computers change the economics of information work. That's the thesis. But here's the grounded takeaway. The most exciting thing about Tesla Optimus isn't any single demo. It's the direction of travel: steadier walking, more natural posture, more capable hands, and a clear focus on tasks that matter. When you see a humanoid robot quietly improve at the boring stuff, carrying, placing, sorting, repeating, that's not boring at all. That's the path to real usefulness. And if Optimus keeps moving down that path, the question won't be, is it real? The question will be, where do we put the first ones?